Alright, in this video installment we're going to be learning about waves, which is the beginnings of one of my favorite topics, which is sound, or of two of my favorite topics to teach about, which is sound and light. So hopefully you enjoy learning about these also. So the first thing before we understand waves is we have to understand what a vibration is, because every wave starts with a vibration. Okay, so a vibration is when we have an object that's moving about what's known as its equilibrium point. So if you think about this bobblehead that's here, the bobblehead moves back and forth. Eventually it will slow down and there will just be one set position that it will stay in until somebody goes and pokes it with their finger. So where it normally sits is its equilibrium point. So what happens is it's got disturbed past its equilibrium point. So you can think about in this graph here where it sits at point A and then I pushed it to point B. And then as it tries to get back to its equilibrium, because it's moving as it gets to equilibrium, it will continue to point D, where it has slowed down enough where it turns around and comes back. And so it repeats that cycle over and over again, approaching equilibrium, passing it, and coming back. Now in the real world, this bobblehead would eventually stop, and it would stop because friction or other things would take energy away from the bobbling head. And so every time it would go, these points would get closer and closer to equilibrium until finally it stops. So as we can see, as something's going, as it's vibrating, you have moments when it's slowing down. So all the places colored in purple here are places when it's slowing down as it reaches that maximum. And then there's times when it speeds up. And so it's speeding up as it's going away from those maximums and back towards equilibrium. So now that we understand what waves are, what exactly is a vibration? Or sorry, now that we understand what vibrations are, what is a wave? So a wave is a rhythmic disturbance in a medium, and it carries energy away from that vibrating object. Okay, so again, real vibrating objects eventually slow down, and that's because waves will carry their energy away. Okay, so it should also be noted that a pulse is when we have a single disturbance moving through a medium. And later we'll see the difference between a wave and a pulse. I'll animate that for you. Okay. When we have a wave, we need to always make sure we understand that the wave is what moves and the energy moves with the wave, but the medium, the material that the wave is moving through, does not move with the wave. So when you see a wave on water, the energy is moving through the water, but the water itself is not moving along with the wave. Yes, it's moving up and down and back and forth, but overall, the water isn't getting moved around. Okay? There are two different types of waves. So this one on the bottom is what we normally think of as a wave, and that's called a transverse wave. And the one on the top is another type of wave, and that's called a longitudinal or compression wave. The two different types of waves arise from two different types of motion that create them. A longitudinal wave goes if the hand or whatever is creating the wave is vibrating back and forth parallel to the direction of the wave motion. Then you get a longitudinal wave, or a compression wave, because you're compressing and stretching out the spring. And then a transverse wave is formed when you move, the disturbance is perpendicular to the direction the wave will move. Okay. So, and there's some different terms that go along with those two waves. In a compression wave, there's areas where the material gets pushed together, and that's called a compression. And then an area where it's drawn out from compared to where equilibrium would normally be, and that's called a rarefaction. And then in a transverse wave, we have instances where we are above the equilibrium position or to one side, and we call those crests. And place where we are below the equilibrium position, we call those troughs. And the size of the disturbance in either case, how much we've disturbed the material from normal, is called the amplitude. Notice that amplitude is measured from the equilibrium position off to just one side. It's not measured from crest to trough, just from equilibrium to the maximum one side. And the amplitude has to do with how much energy the wave is carrying. So waves have many different properties. The first of which was pictured before, is the wavelength. So that's the distance a wave repeats itself over. And if I go back to this image, we talk about wavelength from crest to crest. We could also measure from trough to trough. On a longitudinal wave, it would be measured from compression to compression, or the middle of a rarefaction to the middle of a rarefaction. So longitudinal waves have wavelength also. Waves can have periods, which is how much time it takes for them to repeat, which I can't show you in a stationary picture. We have to look at one where it's moving, and then we'll talk about that one on an animation later. There's the frequency, which is how often the medium oscillates, and we measure that in hertz. A hertz is the same thing as 1 per second. So if a wave is coming by once every second, it has a frequency of 1 hertz. And then we can talk about the velocity of the wave, which is how fast the disturbance moves through the material. Okay, and a lot of times people get velocity and frequency confused, and I want to make sure that that doesn't happen to you. So we're going to look at, here's an example. So I'm going to have, here we have an oscillation. And if I want to measure the frequency, I would just watch one place. So I'd put my cursor in one place. I would go 1, 2, 3, 4, 5, 6, 7, 8. And I would count how many times a wave come by, let's say for 10 seconds. So, and I would take that and how often the wave comes by in 10 seconds. And that would be related to the frequency of the wave. If I wanted to know the velocity of the wave, I would follow along with the wave with my cursor, and I would measure how fast the cursor. So I'd pick a crest, and as best I could, I would follow the crest along with my cursor, and I would time how long it takes my cursor to move a certain distance, and that would be related to the speed of the wave. So again, frequency you measure just by watching one point, and speed or velocity you measure by watching how long it takes to go across. Okay, and again, to see the difference between a wave and a pulse is just one disturbance. So you can see that as the one disturbance goes through the material, that's a pulse. A wave is where it's rhythmic. So if I hit pulse over and over again, I can generate a wave if I do it with a rhythm. Okay, and so there's lots of different things we can change about this simulation to show many different effects. Okay, there's some relationships between different phenomena of waves. So one that's important to realize is that frequency and period are just the inverses of each other. So frequency is 1 over period, or period is 1 over frequency. Okay, so those are very closely related to each other. The other relationship that I want you to know is that how fast a wave moves is equal to its frequency times its wavelength. So frequency and wavelength are inversely related to each other. As frequency goes up, wavelength has to go down. So if I go back here and I look at the oscillations, okay, I'm going to turn damping down just a little bit more. Okay, so one thing you can see right now, if I look at the frequency set to 50, if I set the frequency up, you can see the waves get closer together. And if I set the frequency down, as we slowly dampen out, I mean not quite that far down. Okay, when you see it's lower, then the waves are spread further apart. So there's that inverse relationship between the two. For then, though, again, those of you that are not great at algebra, we can have another super intelligent triangle that helps us relate these three variables, where if I want to know velocity, I cover that up. It equals frequency times wavelength. If I want to know wavelength, I cover that up. It equals velocity divided by frequency, and so on. Okay. We're going to spend a little bit of time talking about what affects speed, but I want to do that through a lab. I don't want to do that through notes. Okay. Another thing I want you to know about waves is waves can interfere with each other, and that can actually lead to some really cool things happening. So I can take two different waves that are both what it's called in phase, which means they're on the same side. These are actually not two waves, but two wave pulses. So they're on the same side of the material, so the disturbance is the same way. When they overlap, they will create a larger area of interference. Okay, and that will not stay there. As they continue to pass by each other, that goes away. And that's called constructive interference. This first one is constructive interference because you have two things adding together. I can also interfere destructively, where I have now my pulses are on opposite sides, so they're opposite disturbances. So when they come together, they create this green thing. So the red is partially canceled out the blue, but the blue is a bigger disturbance. And then after interference again, they just kind of travel on their merry way. Okay, and whoops, that's a bad example because that was not the same before and after. So sorry there. Afterwards, it would just look like the red and the blue, only they'd be flip-flopped. So don't go with that original drawing. Because of interference, you can get what's called a standing wave. And a standing wave is when you get your wave to travel along the material, and the frequency the wave happens at is just right so that the wavelength of the wave matches the size of the material. So the wave fits on the material in like perfect set increments. And so when that happens, you get some areas which are called nodes. So if you can see, if I can get my cursor in the node just right, you'll see it's always in contact with the wave. And I don't think I have it quite there. But that's what a node is. And so in essence, you can think of just that point as not really moving. Okay? Because you're always getting destructive interference at those points as the waves come in and other waves bounce back and hit. The waves are always out of phase with each other, and so they're always interfering destructively at those points. The other points, the points where you get maximum disturbance, you have varying amounts of constructive interference up to the maximum amount of constructive interference. And so sometimes when the waves come together, they're completely in phase with each other. Sometimes they are out of phase, but sometimes, again, they are completely in phase with each other. And so you get what's called the anti-node, so the place where you move the most. Okay? And so we'll be talking about standing waves, especially when we start talking about musical instruments, because standing waves are really important to how musical instruments work. Well, that's all for our wave introduction. And so hopefully you got a lot out of this, and tomorrow you'll be working on a worksheet related to it.